Okay, so today we start Chapter 8. This is Section 3 of Chapter 8. We're jumping right in on hypothesis testing. So it's a little bit different than anything we've done before. So you really need to get the structure of the test and all the little details, and then be ready to write a couple of sentences for your conclusion. So this is going to require a couple of sentences for it to be complete, for the problem to be complete. So you can see that I've divided it into a four-step process. That's how I will count it when I'm grading. I will be looking for those 4 steps and give you partial credit for whatever you have right and whatever you have wrong within those 4 steps. Okay, so we start off with a scenario, and then we are going to follow the 4-step process to get that scenario into what is called a hypothesis test. Okay, so the Spike Network commissioned a telephone poll of randomly sampled U.S. men. Of the 712 respondents who had children, 152 said yes to the question, "Are you a stay-at-home dad?" Okay, an advertiser of baby-carrying slings for dad will buy commercial time if at least 25% of men are stay-at-home dads. Okay. Could Spike claim, and I've highlighted that word claim because that's important to your success here, is that you can identify a claim. Could Spike claim to the advertiser that at least 25% of men with young children are stay-at-home dads? We are going to test this claim, and we are going to use the sample that is given and what is called a significance level, which is often lettered with the letter alpha for Greek letter alpha. That's the significance level called alpha. Okay. The first thing, in the first step, it says, define all the variables, write a claim, the null, and the alternative hypothesis. Okay, so here are step 1. This is step 1, defining all the variables. Now, this little sub-zero here, I'm going to explain that in just a moment, but this is what comes from the claim. So the claim is the at least 25%. So you see that that's matching the 25%. I'll tell you what that subscript means in just a minute. This next one, we've seen this one before, p hat, and it's still calculated the same way, x over n. X being the number of successes in whatever scenario we're looking at, and n being the total in that sample. So in this case, p hat is 157 over 712. And when that's divided out, it's 0.22. Okay, 150, that actually is the wrong number. Okay, so it's better if I change it here. Okay. Sorry. Okay, so that should be 157 and 712. I'm going to make sure that division is correct and that typo is not more extensive than that. Okay, so we're using the 157. So if p hat is 0.22, then again, not a new term. Q hat is the complement, or 0.78. This is alpha 05, came from the problem. And I will talk about this z in just a moment, too. Okay, we want to write a claim, and we want to write it in math symbols. Okay, so the claim that at least 25% of men are stay-at-home dads is written this way. Claim, proportion, P, greater than or equal to 0.25. Okay, greater than or equal to is the same as at least. At least means that number that you're talking about and higher. So, greater than or equal to 0.25. Now, once you have a claim written, this is a very important step. The next is to write what we call the null hypothesis. This H stands for hypothesis. That subscript 0 is actually null. Okay, that is meaning 0 or none or nothing, but we use a 0 for it. So this is the null hypothesis when it has that subscript of 0. Okay, then I put in the P and I've added that subscript of 0. Okay, meaning this is the null hypothesis proportion. Okay, we have a couple of rules. a very specific rule for the null hypothesis and this sign. In the null hypothesis, the sign must include equal to. It must include equal to. It can be less than or equal to, greater than or equal to, or just equal to. Those are your only three choices. So the sign must be either greater than or equal to, less than or equal to, or just equal to. Only three choices. And it is based on the claim. In the claim, if the equal to sign is there, then this claim automatically goes into the null hypothesis. So they should be the same. They are only going to be the same if the equal to sign is in the claim. So you'll see a case where it's not, and I'll tell you what to do then. But if the equal to sign is in the claim, then that same sign goes into the null hypothesis. The value of 25% is going to go all the way through this. Once you've decided what your claim value is, it stays with the null, and it stays with the other one, which is called the alternative hypothesis, H sub 1. Okay, that's our first alternative hypothesis. We're only going to do one. So H sub 1 is the alternative hypothesis. And the rule here is that must be the opposite. The sign must be opposite of the null sign, the sign in the null. Now, can everybody see that the sign in the null, greater than or equal to, the opposite of that is less than? Okay, that covers everything. That covers every possibility within those two signs, greater than or equal to and less than. So the equal to sign cannot ever be in the alternative. There will never be an equal to sign in the alternative. So the choices for the alternative are less than, greater than, or not equal to. Those are the only choices you have for the alternative, the inequality that's in the alternative. Okay, I know this is a lot to process at once, but that's why I expect you to watch this little video more than once. Okay, and I will be doing more than one example here. Okay, then I kind of go over those rules again. The null hypothesis always contains the equal sign, either by itself or with an inequality, and the claimed value. So the 25% is in both. The alternative hypothesis is always the opposite of the null. And by opposite, I just mean the inequality sign. Okay, the inequality sign is the opposite. Okay, step 2. I'm going to look back here at what it says to do. It says draw a normal curve. Now, when I say that, I mean do this. Just draw a little curve. Okay, it's already drawn on this example, but you're going to just draw that little curve. And remember, what's in the middle of that curve? 0 is always in the middle of that curve. Okay, so if you draw it like that, you're fine. Then, using the significance level or confidence level, and really in this case, it's going to just be significance level, you're going to identify the critical value and shade the curve showing the reject region. Okay, now here's where we go to the table. We have a significance level of 0.5. Alpha equals 0.5. Okay. This is what we call a one-tail test. One-tail test. Do I need to zoom in a little bit here? Okay, it's kind of tiny there, but you have it in front of you. This is a one-tail test. This is really hard to see, too. I'm sorry that it printed this way. Okay. This line is where the critical value is, and I want to show you what the table looks like in this. Everybody have your table? But this table is very helpful for this. If you look at the top of the table, the last section we did, we had the level of confidence here at the top. Now look what we have in the next two columns, our rows. We have one-tail alpha and two-tail alpha. Okay, so this particular one is a one-tail problem. We're looking at over at 0.5, And there's 0.5. The significance level is right there, alpha, 0.5. And then because it's a z, we go all the way to the bottom, and that's where 1.645 comes from. Now, this particular problem is what we call not only one tail, but it's a left tail. And it's a left tail because of this inequality sign in the alternative. Okay, so the alternative inequality dictates whether it's one tail, two tails, left tail, right tail. I wish I could come up with more to rhyme with that. This one is a left tail, and see it's shaded out here, and I know the whole thing looks like it's shaded. It was actually different colors. So the shading should only be it should be shaded to the left like this. So I tried to do it in this green, kind of outside the lines, but it's shaded to the left. And it's shaded from negative 1.645. Now, all the values on this table are positive, but if you have a left tail, that automatically makes that a negative number. That's a negative number. Okay, so you will need to recognize that. This is what we call the reject region. So our z that we got from the table identifies the reject region. It's called a critical value. That's what z is called now, critical value. This z is called a critical value, and it determines what we call the reject region. And we're going to use that reject region to come to a conclusion about this test and whether or not the claim was true or valid. Okay. Now we have another z, and sometimes it's difficult to get these separated from each other, and there'll be different notations in different textbooks. I think this textbook uses for the critical value, it might use a subscript of c to identify that it is critical value. Take a look at that. You need to just associate the significance level with that critical value, and then shade your reject region and list it, what it is. Okay, these are the things I'll be looking for when I'm grading a problem, is whether that reject region is correct number in the correct place. Okay. Next, we're going to do some calculations. Step 3 says, using the appropriate formula for the variables that we have, calculate the test statistic. Okay, let's go to the formula sheet. Although I have the formula written down here, when you're taking these tests, you have to know what's on the formula sheet. This chapter, we're going to be using these 3 formulas from the formula sheet. See them, the 3 of them. Notice that these 2 on the left both have x bar. What does x bar mean? Mean. The mean. Okay, do we have a mean in our problem? The word mean was not in our problem. Our problem has p's and q's, so we're using this one. Okay, that's how you tell which one to use. And when I say in that step that I say use the appropriate formula for the variables you have, if you don't have a mean in the problem, don't use this problem. Don't use the one with the mean if you don't have a mean. If you have p's and q's, you use the one with the p's and q's. Okay, so this is the formula that we're using today. Actually, these are the last 3 that we're going to use. Okay, this one is in, if you need this little bit of help, section 8.3, and this will be 8.4 and 8.5. This t is just like with the confidence interval when n is less than or equal to 30. And this z is when n is greater than 30. Okay, but we'll get there next time, or later in the week. So 8.3 is the hypothesis test for the proportion, and this z is called, as this section says, a test statistic. It's called a test statistic. So when we get back to the example sheet, the test statistic z for the proportion is calculated as follows. All right, if you have a calculator, scientific calculator right now, I suggest you practice with your calculator to make sure that you can get this answer, okay? So that it doesn't become an issue later on that you just can't calculate right. You could do this all at once, but the trick is if you do it all at once on your calculator to put parentheses around that top part, around the numerator. So here's what it looks like if you try to do it all at once. So open parentheses, 0.22 minus 0.25, close your parentheses. So it's doing the division for that whole difference. Divided by, and now I'm going to open up the square root sign and just do that multiplication and division. 0.25 times 0.75 divided by 712. Woohoo, you got it? Yep. Woohoo, I got it too. It's okay. So just everybody should make sure that you can get the calculator to get this answer. Okay, so that you don't get stuck with just a calculation issue. Let's match up these values with the values that we wrote down. So p hat from the problem was the x over n and came out to be 0.22. This p sub naught, or p null, if you will, came from the null hypothesis. Okay, that's why it's identified. We have all these p's and q's in here, so we have to identify them somehow, separate them from each other. So because of that 0, that subscript 0, that means this number needs to match that number. So 0.25. So that's why it's so important that you write this stuff down first. You get all of this stuff written down before you try to calculate, because you'll get these reversed. You get these two reversed, you get a negative when you should have a positive, or a positive when you should have a negative. And it will mess things up. So you want to be very careful at this point. Question?
You got negative 1 point something, right?
Uh-huh.
Yeah. I got negative 15.18.
Okay. So something went wrong. I'll show you again in just a moment how to calculate it. Something went wrong with probably your grouping symbols. Okay, so then this P and Q, again, they have the zeros, which means they come from the null. So 0.25 and 0.75. And then N comes from the original problem, 712. All right, so everybody good with that? How about the practicing? Are you practicing? Everybody able to get that? Paul, were you able to get the number?
Yes, ma'am.
Okay, perfect. All right, the importance of this test statistic, and this is another thing you have to show on your curve. I want you to show where that is located on the curve. So I'm going to put a bunch of arrows here, but you can just say where it's at. It falls to the left of the negative 1.645. So it is out here in the reject region. Does everybody see that that negative 1.849 is to the left of negative 1.645? So it's in that shaded area that I shaded in green. And it is to the left, therefore it's in this reject region. So, what does that mean? My next sentence in my conclusion tells you what that means. Since negative 1.849 is in the reject region, the null hypothesis is rejected. Okay, this is always your first sentence. We are either going to reject the null hypothesis or we are going to fail to reject the null hypothesis, all based on where that test statistic falls. Does the test statistic fall in the reject region or in the non-reject region? Okay, if it falls in the reject region, then we reject it. So let's go back and look at what we're rejecting. We are rejecting that the proportion of men who say they're stay-at-home dads is not, that it is greater than or equal to 25% or at least 25%. We are rejecting that. Okay, so we say no, that's not true. The stats that we have, the sample that we have says no, that's not true. So now matching that to the claim, since the claim and the null are matching, we are also rejecting the claim. So sometimes it'll be just the opposite. Just depends on what's going on in the problem and what all your inequalities are. In this case, because we are rejecting the null, we are also rejecting the claim because they're the same. Does everybody see that? So my next sentence says, Spike cannot claim that the sample shows 25% of men with young children are stay-at-home dads. Okay? We can't, and I'm just writing a sentence kind of responding to the claim from the original problem and saying whether they can make that claim or not. You can also say something like, there is no evidence to support Spike's claim, or we reject Spike's claim, something like that. You are just saying that the claim is wrong based on the sample that we have. All right, that was a full test. That is a hypothesis test. Now, I spent a lot of time talking and saying what things were. So it should go, when you start practicing this, it should go much quicker than how long it just took me, what, 21 minutes? Oh, my goodness. That is crazy. All right, I'm going to turn it over and do the next example. I'm going to try to do a little less explanation, but you know what, it's hard for a teacher to not explain things. So it still may take a little while. This one also did not run off very well. The colors here, you can see where I have the critical values listed are the lines. If you want to do that for yourself. I do have a highlighter. Maybe that'll be better. Yeah, helps a little bit. Okay. A company is willing to renew its advertising contract with a local radio station only if the station can prove that about 20% of the residents of the city have heard the ad and recognize the company's products. The radio station conducts a random phone survey of 400 people, and it finds that 75 have heard the ad and recognize that company's product. Does the radio station have enough evidence to claim that 20% of the residents have heard the ad and get the contract renewed? So the question is, does the radio station have evidence to support their claim that 20% of the residents? So here's the claim. There's the claim. So you want to make sure that you know what the claim is from the problem first, and how to turn, that into an inequality. Or in this case, equals. It's equals. Okay. We're using a significance level, alpha of 0.01. So, step one, writing all the information down. Okay, so the 20% claim goes with the null proportion. The sample, x over n, is 75 over 400, which I have rounded to 3 decimal places here. So this is p hat, therefore q hat, and again, this was just subtraction from 1 to get q hat. And now a listing of O1 as the alpha. At this point, you have a choice of figuring out what z, this time I put a little star by it, indicating that it's a critical value. Again, different textbooks use different ways to indicate critical values. So I've had one in the past that used that star. Okay, here's that claim. Very important that matches. 20%. They don't say more than or less than or at least or at most or anything like that. They say that it's 20%. So that gets us the equal sign. Following the rule, the equal sign goes into the null hypothesis. So the claim and the null match here. The claim and the null match. Therefore, the alternative is going to have the not equal sign. It has to be the opposite of the null. So we have everything written out here. Now, remember when I said left tail, right tail, one tail, two tail? All right, this is a two tail. And this is the only one that's a two tail, not equal to. Because they don't say less than or greater than. It's just equal and not equal. So this is what gives us two reject regions, a left tail and a right tail. Okay, so going to your T-distribution table, our alpha is 0,1. See the two tails? Two tail alpha, 0,1, all the way to the right, then all the way to the bottom, where our Z is. All right, 2.576, and that goes in both the left and the right, because there's a negative and a positive. So this creates two reject regions. So you list both of them. And again, the only time this happens is when you have the not equal to sign in the alternative. So we have two reject regions. This is a two-tail test. Same Z test statistic. Got to get these values in where they need to be. P hat minus P sub 0 from the null. Then also from the null, 0.2 times 0.8, all divided by 400. Okay. Again, practice calculating this real quick, guys. You need to make sure that you know how to do it. I would put, if you want to do it all in one entry, you need parentheses around the numerator. Can you see it? Yeah. And verifying that that is negative 0.6. Now, negative 0.6 is very close to 0. So when we locate that negative 0.6, it is right up here somewhere. Negative 0.6. Is it in the reject region? No, it's not even close to the reject region. So that means, looking back at the null hypothesis, we are not going to reject this. Okay, you're going to love this. When we, I don't even use the fail to reject statement. Okay, so in the book, you're probably going to see the term fail to reject. Often that's what we say when we have to keep the null hypothesis, when we have evidence to support the null hypothesis. Okay, so here's what the conclusion is. Now, guys, these conclusions, I want you to keep this piece of paper because your conclusion needs to be written this way. It's two sentences. The first sentence is saying whether you're rejecting or failing to reject the null hypothesis and why. And the why is since negative 0.6 is not in the reject region, the null hypothesis cannot be rejected. Okay, that's sentence 1. So now we look at the null hypothesis that we're not rejecting. We look at the claim. Okay, we're not rejecting that either. They're the same. Okay, we look at the problem. And the question was, does the radio station have evidence to claim that 20% of the residents have heard the ad and to get the new contract? And it looks like they're right. So here it is in Stat Talk. The radio station has statistically significant evidence that about 20% of those surveyed have heard the ad and recognize the company's product. So this is what they're presenting to that company as evidence that, yeah, 20% of the people listening have heard your ad, and they recognize your product. So please, let's have a new contract, okay? It's going to cost you even more because 20%, although 20% seems a little low to me. Okay. Any questions? Yes.
Where exactly did you get the Z from, and why is it so
Okay. Question was, where did Z come from? All right, so we're starting with the alpha of 0,1. This is an extremely important question, everybody. So looking at the T-distribution table, we've determined that it's two tails. Two-tail alpha all the way over here to 0,1, and then straight down to the bottom.
Okay, so So you always go straight from 45.
Yes. In this case, because we're using Z. Okay?
And it's over 30.
And it's a proportion. The proportion is always Z. Okay, the only time we have a question is when we have a mean, and it might be less than 30, but we'll get there. All right, so, and it's plus or minus because there's two tails. There's a negative and a positive.